Oh, thank you. So I'd like to thank the organizers for the invitation to speak here, as well as to be part of this wonderful program at MSRI. It's always a pleasure to be here. So I'm going to be talking about some attempts to develop geometric structure-preserving discretizations in the context of field theories, particularly field theories with gauge symmetries. And I'll be concentrating on the applications to general relativity and describing some, it's like analytical tools we've developed. It's like which allow you to preserve certain symmetries of the problem. And this is joint work with Evan Golick, who's now at the University of Hawaii, James Hall, and Joris Vankerschafer. It's like now both in industry. And it's been very generously funded by the National Science Foundation and more recently by the Air Force. All right, so let me sort of try to set the context for this problem. A lot of the motivation for studying this is motivated by some recent developments in gravitational wave physics. So in particular, gravitational waves are ripples in the fabric of space-time, which were predicted by Einstein back in 1916. And the first direct observations of gravitational waves happened, it's like on September 14th, 2015, and this was part of the Advanced LIGO project, and for which I guess the Nobel Prize in Physics was awarded. And there is a sense in which a lot of this was enabled by basically numerical simulations, it's like which were able to construct gravitational wave signatures, which would then sort of allowed you to extract the signatures from the signals. Okay, so in particular, it's like numerical relativity plays an important role in this because what you want to do is ultimately you would like to solve the inverse problem. You detect gravitational waves, but you would like to use this as an astronomical tool to, figure out it's like what celestial objects it's like are interacting with each other. And so you have to, in order to solve the inverse problem, you first have to have a very good forward solver. And so in particular, numerical relativity plays that role in computing black hole mergers, which are then typically responsible for gravitational waves. So the setting for this is the Einstein equations, and there's a way to describe this in a Lagrangian formulation using the Einstein-Hilbert action. And this is a action which is defined on Lorentzian metrics, and some things which are relevant to note is that it's a second-order Lagrangian in the sense that it involves second derivatives of the Lorentzian metrics. And the corresponding Lagrange equations are the Einstein field equations, which are given here. So as I said, it's a second-order field theory, but in addition to that, it's a gauge field theory. So there are local symmetries of the problem, and that has implications later on, both in terms of the mathematics as well as the computation. Okay, so a gauge symmetry basically is a continuous local transformation which leaves the system physically indistinguishable. It's local in the sense that it's not like it's like a transformation, it's like which is the same everywhere, but it depends on where you are in space and time. And one consequence of this is that when you look at the Lagrange equations, they are in some sense underdetermined because the evolution equations in and of themselves are insufficient to propagate all the equations. And what essentially happens is that you have to augment the evolution equations with certain constraint equations in order to propagate the solutions forward or to give you a well-defined solution. And the gauge symmetry also sort of partitions up the variables into two general classes. There are what are known as kinematic fields, which are the symmetry variables, and they have no physical significance. And there are the dynamic fields and the conjugate momenta, which carry all the physical information in the problem. On the other hand, the Lagrange equations are in some sense overdetermined as well because you don't have the freedom to arbitrarily specify the initial data. And so it's like when you specify the initial data on a Cauchy hypersurface, then that initial data has to satisfy some sort of constraint as well, and typically that takes the form of an elliptic PDE. So there's a sense in which these symmetries result in degenerate systems, and one could potentially describe this using what is known as multi-Dirac mechanics in geometry. So Dirac mechanics is a generalization of symplectic and Poisson structures, or Dirac structures are a generalization of symplectic and Poisson structures, and they're particularly useful for describing degenerate problems, and I'll describe why in a little bit. Okay, so let's look at an example of this. So let's say you have the E and B fields, the electromagnetic fields, and you want to write down Maxwell's equations. Okay, so you can write down Maxwell's equations in terms of the scalar potential and a vector potential, and you get equations which look like this. Okay, and it's easy to, and the sort of that box operator is just the wave operator, and you can easily check that if you transform the scalar potential and the vector potential in the following way, where f is some scalar valued function of time and space, right? Then the equations remain invariant. Okay, so this is an example of a gauge symmetry, and associated with this gauge symmetry is a constraint on the initial data. So you can't arbitrarily specify the initial data. They have to satisfy these conditions, where the superscript bracket 0 just means that the field's on the initial surface. Okay, so you have this indeterminacy. It's like due to the gauge freedom, and the way you choose in some sense, a well-defined solution of this is you pick a choice of gauge. And so there are many choices of gauge in electromagnetism. One of them is the Lorentz gauge, which is given here and leads to the following version of Maxwell's equations. And alternatively, you could pick something like the Coulomb gauge, which gives you a different form of the equations. So if you ever try to solve Maxwell's equations analytically, then you know that picking the right gauge makes your life extremely simple, and picking the wrong gauge makes your life extremely complicated. But a priori, there's no reason to prefer one over the other, and you sort of need to know what the solutions behave like in order to have some insights to which choice of gauge to choose. So why is that an issue? That's an issue because when you're doing computation, typically the reason why you do computation is because you don't necessarily have a very good idea as to how the solutions are behaving. And even if you do have some idea as to how the solutions are behaving, there's no reason to believe that a global choice of gauge is the right one. So the real question then is, when you have problems with gauge symmetries and you're trying to do computation, does it actually make sense to pick a gauge that's like ahead of time in a global way, or is there some way to incorporate the choice of gauge in the actual computational process as well? Can you somehow adaptively choose the gauge, right? So those are some of the questions which we haven't really answered, but I think which need further study. Okay, so in any case, one consequence of symmetry is its connection with conservation laws via Noether's theorem. So every continuous symmetry of an action, there exists a quantity which is conserved in time, which is known as the Noether quantity. All right, so the simplest example of this comes from classical mechanics. And for example, if you have a time-invariant Lagrangian, then associated with that is the Hamiltonian, which is typically identified with the energy. And so you can easily show that if you have, again, a time-independent Lagrangian, then it's like the Hamiltonian is invariant of the flow. Okay? So more generally speaking, if you have a gauge field theory, then associated with every one of these local symmetries is a Noether current, and the Noether current obeys a continuity equation. And if you integrate this Noether current over a space-like hypersurface with the appropriate boundary conditions, then you end up with a conserved quantity known as the Noether charge. So the Noether currents for electromagnetism are given as follows, and then associated with the Einstein-Hilbert action for general relativity, you obtain the stress energy tensor as the Noether quantity associated with space-time diffeomorphism symmetry. Okay. All right. So what are the consequences of gauge invariance in general relativity? So there's a perhaps less well-known version of Noether's theorem known as Noether's second theorem, and it basically says that as I said, the Euler-Lagrange equations are not functionally independent. And so in particular, what happens is that when you look at the Einstein equations, there are basically 10 components of the Einstein equations, but only 6 of them are functionally independent. Okay? So numerically speaking, what people typically do is they pick some 6 of those things, and then they evolve the solution forward in time, and then they use the remaining 4 equations as error indicators, and that tells you when you've drifted too far off the constraint manifold in some appropriate sense. And if you're drifting off the constraint manifold, then you do some sort of adaptive mesh refinement. That's all great, except that the constraint violations grow exponentially fast. And so what happened in the past was that the constraint violations grow so fast that when you do adaptive mesh refinement, you would not be able to sort of simulate past a finite time. So you would have kind of a Zeno phenomena. Okay, so those are some of the issues that one has to deal with. And again, what you do, it's like in order to deal with this is you impose these gauge conditions. And in relativity, it's like there are things like the maximal slicing gauge, or the Didonder or harmonic gauge. And in particular, the Didonder gauge is Lorentzian invariant, and it's particularly appropriate when you're studying gravitational waves. And when you formulate this as an initial value problem, then this Cauchy data, as I said before, is constrained, and the constraint equations are what are known as the Gauss-Kardashev equations. Okay? So because of the fact that there are now different sort of equivalent solutions, if you will, it's like because of the gauge degree of freedom, you have a variational problem which is in some sense degenerate, right? There's no unique extremizer of this. And so the question is, how do you construct a formulation, it's like which somehow automatically gives you the constraint equations so that you have a well-defined method. Okay, so let me say something about what it means when you try to do numerics in this. So the general covariance of the Einstein equations are really a fundamental aspect of general relativity. So you want something which respects the space-time diffeomorphism symmetry. And what that implies, if nothing else, is that it's artificial to choose a global slicing of space-time, right? There's no unique, there's no sort of canonical choice of slicing of space-time. And in particular, it's like if you try to do this globally, then you constrain the kind of topologies of space-time you can deal with. So this is something you really don't want to do. And so that naturally leads to unstructured meshes on space-time. And in particular, it's like what we're going to try to build this approach on are sort of simplicial space-time meshes. Okay, so now you don't have, again, any kind of distinguished sort of time direction here. And then the other thing we'd like to do is we'd like to construct numerical methods which respect this connection between symmetries and conservation laws. So in particular, it's like there's been a lot of success in constructing integrators for Lagrangian and Hamiltonian systems based on discretizing variational principles. And we're going to adopt sort of that approach, but in some sort of more generalized sense. So we're going to consider what are known as Multi-Dirac mechanics, which is based on a Hamilton-Pontryagin variational principle. And I'll say, as I said, why this is appropriate for degenerate problems. In the discretization, you have to respect the symmetries because we have meta-theorems which basically say that if your discretization respects the symmetries, then there are automatic conservation laws associated with that. So there's a discrete version of Noether's theorem, but in order to take advantage of the discrete version of Noether's theorem, you have to construct a discretization which respects that symmetry. And so in particular, it's like we have what are known as sort of gauge invariant discretizations. And then because of sort of this discrete Noether theorem, that results in some sort of multi-momentum conservation law. Okay? All right. So let me first talk about Dirac mechanics, which is a generalization of Lagrangian Hamiltonian mechanics, if you will. And unlike Lagrangian mechanics, which is defined on positions and velocities, or Hamiltonian mechanics, which is described in terms of positions and momenta, we're going to look at what is known as the Pontryagin bundle, which has as local coordinates positions, velocities, and momenta. Okay? And this Hamilton-Pontryagin principle is given as follows. It's really the usual Hamilton's principle, but you relax the condition that the velocity is the time derivative of the position. So I think of v and q as formally being independent, but I reimpose the relationship between the two of this via a Lagrange multiplier term, where p should be thought of as the Lagrange multiplier. Okay, so you're imposing the second order curve condition that v is equal to q dot using a Lagrange multiplier p. So it's easy to convince yourself via the Lagrange multiplier theorem that this is equivalent to the usual Hamilton's principle. Okay, so you might ask, it's like what value there is. It's like in adopting this variational principle as opposed to the usual Hamilton's principle. So let me see what happens. All right, so you do the usual, it's like calculus of variations kind of calculation, and it's like, and you write down, it's like what happens when you take variations in q, v, and p, where the variations in q, it's like vanish at the endpoints. Okay, and you get what are known as the implicit all Lagrange equations. So if you write this thing down, then again, if you eliminate the v's and p's, then it's clear that this gives you the usual Lagrange equations because it just says that the time rate of change of dl dq dot is equal to dl dq, right? So that's the usual Lagrange equations. But in particular, what you see is that the Legendre transform is explicitly there. Okay? So the reason why that's significant is if the Lagrangian is not hyperregular, for example, if the Lagrangian was only linear in the velocities, then this condition, right, that P is equal to dl dv, right, becomes a constraint. It becomes what's known as the primary constraint. So you've explicitly included the primary constraint as one of your equations. And so even when you have a degenerate problem, this system of equations, it's like, can still be sort of propagated forward in time, whereas the usual or Lagrange equations would have degenerated from being a second-order equation to a first-order equation, and then you don't have enough information without explicitly imposing the primary constraint condition. So that's one of the reasons why you might consider using this Dirac or Hamilton-Pontryagin framework when you're trying to look at degenerate problems. Okay, so now I'm going to try to generalize, it's like this idea, the PDE setting using what is known as multisymplectic geometry. And so what we do in this setting is that, so essentially what the difference between the multisymplectic formulation versus the sort of instantaneous formulation of Hamiltonian PDEs is the following. So typically, what one does is that you look at a Hamiltonian PDE as essentially an infinite dimensional Hamiltonian system, and the independent variables are just time, and then it's like your configuration variables are maybe some function which tells you what the field values are at a given time, right? So this is sort of an infinite dimensional point of view. Alternatively, you can think about it, you can think of the independent variables as being both space and time, and then over that you have the fields. And so now you have a finite dimensional theory over space-time. Okay, so this is what we're going to do. So think of this thing at the bottom as space-time, and the fields are going vertically, all right? And so a configuration basically, this kind of bundle gives you what is known as a configuration bundle, all right? And a particular configuration in this configuration bundle is just a section. So more or less what it is something which, given a point in space-time, it gives you that same space-time point, comma, the field value at that point, okay? And so that gives you a candidate, it's like solution of the PDE. And so the next thing you want to do is you want to compute the first derivatives of this. So this lives in what is known as the first jet bundle. It's like associated with this configuration bundle. So it involves all the first partials of fields with respect to the space-time directions. So now you're ready to add some physics to the problem. So you do this by introducing a Lagrangian density, which gives you a map from this first jet bundle to n+1 differential forms on space-time. Okay? So if you can compute this, it's like on a section or on the jet extension of a section, then you can integrate it over a space-time domain to give me the action associated with the problem. And then, so that's written here. You integrate, it's like over a space-time domain, it's like the Lagrangian density evaluated on the jet extension of a particular configuration. And then Hamilton's principle states that a variation of this action is stationary, subject to fixed boundary conditions. So this is the way you describe, or one way to describe Hamiltonian PDEs in this multisymplectic setting. Okay, so now what I want to do is I want to do the same thing I did before, where I relax this relationship between the first jet variables, it's like, and the derivatives. Okay, so I have a Lagrangian density, which is evaluated on a point in space-time, the fields, and then the partial derivatives of the fields with respect to the space-time directions. These are what these VA mu terms are. And then I'm going to reimpose the relationship between VA mu and the partials of y with respect to x via this Lagrange multiplier term. Okay, and then this P mu A is multi-momentum in some appropriate sense. So this yields the implicit all Lagrange equations. And as before, if you eliminate the momentum variables and the velocity variables, you get the usual sort of Euler Lagrange equation. It's like for this multisymplectic formulation of Hamiltonian PDEs. And then there's also a Legendre transform. It's like, and what's interesting about the Legendre transform is that because the sort of the dual jet bundle is affine, there's also a piece that's like which looks like the energy, right? So the Legendre transform basically both encodes the momentum as well as the energy in the problem. Okay, and so all of this is described in this paper in JMP back from 2012. And so now what we want to do, all right, in this sort of abstract framework, what we'd like to do then is to construct a sort of systematic structure-preserving discretization of this. Okay, so because of this fundamental the gauge symmetry, you want to construct discretizations with respect to gauge symmetry and its associated conservation laws. So this falls into the general category, it's like of geometric integrators. So they're basically numerical methods which preserve certain geometric properties of the problem So examples which you might have heard of include sort of symplectic integrators, it's like, or momentum preserving integrators. Other times, it's like the configuration spaces you're working with have some sort of Lie group or homogeneous space structure, and you might want to have numerical methods which automatically stay on that as well, right? So those are just some examples of geometric integrators. And the intuition or motivation for studying these kind of methods is that they typically result in numerical simulations with better long-time numerical stability and better qualitative agreement of the exact flow. And one way to sort of think about this is that, you know, each of these geometric invariants, it's like give you constraints, it's like on the space of possible solutions, and the more you respect that, the better it is. Another way to think about this is that whenever you try to extract information from long-time numerical simulation, then the only hope, it's like the only thing which you can reliably extract out of a simulation like this are things which are in some sense structurally stable, okay? So what I mean by that is that there's this concept in numerical analysis known as backward error analysis, which basically says that if you have a numerical method, there you can think of that numerical method as being the exact time flow of a modified differential equation. Okay, so more or less, it's like when you try to extract information out of simulation, then you have to be extracting properties which are stable with respect to those kind of perturbations, it's like to the equations which come from the modified equations. Okay, so you might then ask, well, okay, if that's the case, what value is there to geometric structure preservation? And the value, if you will, is that when you use a geometric integrator, the class of perturbations which these modified equations come from is somehow constrained, right? So if you have a symplectic integrator, it's not an arbitrary perturbation of the original Hamiltonian system, but it's a Hamiltonian perturbation of that original system. So hopefully, by restricting the class of perturbations which you have, the notion of structural stability, it's like, or the class of things which are structurally stable might be enlarged, right? So that's sort of a hand-wavy, it's like reason for this, but that at least gives you some idea as to why you might care about such things. All right, so how do you construct one of these symplectic integrators? So one way to do this is through this kind of variational perspective. So you have the usual Hamilton's principle, which states that if you have an initial point and a final point, and you want to look at the trajectory which joins that, that trajectory is an extremizer of the action integral, which is the integral of kinetic minus potential energy, and it's stationary with respect to variations which vary the curve in the interior but leave the endpoints fixed. Okay? So one way to discretize this is to imagine sampling that curve with a bunch of control points, okay, and then allowing you the flexibility to move the interior control points. Okay? But in order to do that, of course, you need some approximation of the action integral. And one way to write down an approximation of the action integral is to introduce what is known as a discrete Lagrangian, which is the following object. You should think of it as an approximation of the action integral, but over just a small time step. And in particular, it turns out that what you want to do is you would like to approximate what is known as the exact discrete Lagrangian, which is the action integral evaluated on this distinguished curve Q01, which satisfies the Lagrange equations in the interior from 0 to h, and it satisfies the boundary conditions which are associated with those choices of points. Okay? So of course, it's like that exact discrete Lagrangian is not computable. All right? This is really Jacobi's solution of the Hammett-Jacobi equation. But nevertheless, it's like one can construct computable approximations and say something about the errors associated with your numerical method by analyzing the extent to which your computable approximation approximates this exact object. Okay? All right. So in any case, it's like say I have this discrete Lagrangian, then what I want to do is discrete Lagrangian, which is an approximation of the action integral over just say a pair of points. In order to approximate the complete action integral, you have to sum over those points. So that's what I do here. All right, and then I want to take variations of this action subject to keeping the endpoints fixed. Okay, so this is the discrete version of Hamilton's principle. And when you write down, it's like the stationarity conditions for this, you get these equations, where the d sub 2, in this case, just refers to differentiating with respect to the thing in the second slot, which is just qk. So you should read this as the partial respect to qk of LD qk minus 1 qk, and this thing is the partial respect to qk of LD qk qk plus 1. Okay? So if you look at this thing, it's like you can think of this as a two-step method or one-step method on two copies of Q. So in any case, it maps pairs of points, qk minus 1 qk to qk plus 1. So it gives you a way to time march the solution forward in time. And if you don't like to think of this method in terms of pairs of points in position, you can introduce momenta. It's like in the following way. And it's easy to convince yourself that this is equivalent to the equation above just by eliminating the momentum variables. And this is, of course, nothing more than a characterization of a symplectic map in terms of a type 1 generating function. So you really should think of this discrete Lagrangian as a type 1 generating function, which you should already have thought of that because that's Jacobi's solution of the Hamilton-Jacobi equation. All right, so, so these kind of ideas have been applied in many problems. So we've applied these things to multi-body systems, which show up in various mechanical problems, fluid structure interactions, and stuff like this. So this is work due to Taeyang Lee, who was a former student of mine, who's now at George Washington University. And Todd Murphy, who's at Northwestern, has applied these kind of ideas to model sort of complex multi-body systems. It's primarily motivated by human prosthetics and biomechanics. Okay? And you can apply some of these ideas to continuum problems, and this is stuff due to Eitan Greenspan at Columbia. Okay, so let me focus on what are the advantages of constructing numerical methods, from this perspective, and what that buys you. Okay, so one of which is this sort of relationship between symmetries and conservation laws. So there's a discrete version of Noether's theorem. Okay, so if you have a discrete Lagrangian, which is G-invariant under the diagonal action. So what I mean is that if I take LD Q0, Q1, and it's the same as what I've gotten if I evaluate LD on G times Q0 and G times Q1, then I say that that discrete Lagrangian is G-invariant. Okay, and so the diagonal action is natural here because this is the natural analog of what you get if you do the tangent lifted action. It's of a group action in Q, right? And then there's if you have a discrete Lagrangian which has this property, then there's a discrete momentum map given by the following, which is preserved by the discrete flow. Okay. So the other thing is that there's this object which we call the exact discrete Lagrangian, which I talked about before. And even though you can't compute it, it exists. And formally speaking, it gives you a way of characterizing the generating function associated with the exact time h flow. Okay? So you can ask yourself to what extent, if you had a computable discrete Lagrangian, if it approximated the exact discrete Lagrangian to a certain order of accuracy, if you knew that, what could you then say about the corresponding numerical methods? And what basically happens that if you have an approximation result like the following, then the corresponding numerical method has the same kind of approximation error. So why is that easier? Why is that a good thing? That's a good thing because, of course, the computable or the discrete Lagrangians are scalar value functions of Q cross Q, right? Whereas it's if you had the numerical method, in general, it could be quite complicated. And so the error analysis that's necessary to establish this result is typically much easier than what you need to directly analyze the numerical method. Okay, so this is what is known as variational error analysis, and it sort of, as you see in both of these instances, we've made fairly general statements about properties of the numerical method based on just properties of the discrete Lagrangian, okay, which are typically easily to check. So now I haven't told you how you actually go about constructing one of these things with the properties which we talked about. So let me say a bit about that. Okay, so one way to express these exact discrete Lagrangians is in the following way. So you can write down the exact discrete Lagrangian as the extremal over sufficiently differentiable curves satisfying the boundary conditions, the extremal of the action integral over these family of curves. Okay, so it's easy to convince yourself this is equivalent to the previous boundary value problem formulation because the stationarity conditions for this extremal problem are just the Lagrange equations. Okay, so what you do to construct a computable object, that is, you replace the family, this infinite dimensional family of curves by some finite dimensional function space, all right? And the other thing you need to do is you can replace the integral by some numerical quadrature formula. And so once you've done that, then you have now a framework where you can construct one of these discrete Lagrangians, which is computable. So the last aspect has to do with the construction of group-invariant discrete Lagrangians. And what you need to do, it's in order to construct a group-invariant discrete Lagrangian in this setting, is to choose finite dimensional function spaces, which are what are called group-equivariant. And the simplest way of thinking about this is that if you imagine you have a way of taking say a sequence of points or control points in the data space and constructing some finite dimensional function space associated with that. So you map data to curves, if you will. Then if that construction respects the following transformation, which is to say that you take the data and imagine you rotated all that data by a fixed rotation, and the new curve, it's like associated those control points is related to the old curve by the same rotation, then we say that that function space is group equivariant. Okay, it's not group invariant because the curves actually do transform, but they transform in sort of the natural way. All right, so if you have a group equivariant function space and a group invariant continuous Lagrangian, then when you construct a discrete Lagrangian in this way, then that discrete Lagrangian will be group invariant as well. Okay, and so because of discrete no-fizz theorem, it will preserve momentum. Okay, so the other thing it's like one would like to show is that I chose some finite dimensional function space in this construction. I want to ask whether or not there's some way to relate the error properties of my numerical method to properties of this function space. Okay, so in particular, it's like one thing which shows up with these Ritz methods is to ask the following. So say you have a continuous solution, which I call Q, and I want to relate. I want to look at the numerical method, which gives me QD, and I want to measure the error. It's like between those two things. If I can say that the error, it's like in my numerical method, is related to some is bounded from above by some multiple of what is known as the best approximation error, which is the basically the minimum error you can make by replacing the continuous solution by some element of the finite dimensional function space measured in some appropriate norm. Okay, so if you have a property like this, then you say that your numerical method is in some sense optimal. Okay, because more or less it's like you've reduced the problem of establishing certain error properties of my numerical method based on error properties of the function spaces I'm working with. Okay. Ideally, it's like if you construct a numerical method which chooses some finite dimensional function space, you would like something like this result to hold. Okay, so let's ask, well, how do you go about, or what kind, excuse me, what a result like this would look like in the context of what we talked about so far. So imagine you have a, excuse me, you have a sequence of function spaces which limit in some appropriate sense. It's like to these twice differentiable curves, and that these function spaces are nested, for example, and you have sort of an increasingly accurate sequence of quadrature rules. So you can imagine then constructing discrete Lagrangians, it's like which are based on this sort of sequence of variational problems, which are in some sense limiting, it's like to a variational problem which gives you the exact discrete Lagrangian, right? Because the sequence of function spaces limit to this twice differentiable curves, and the limit of those quadrature rules limits to the exact integral. Okay, so you could imagine that the variational problems are limiting to this limiting variational problem. So you can ask yourself whether or not these discrete Lagrangians which you have, right, converge to the extremizer of the limiting variational problem. And that's not necessarily the case. Just because the sequence of variational problems converge to the limiting variational problem does not mean that the extremizers or the extremizers of the sequence converge to the extremizer of the limiting variational problem. Because establishing something like this, it's like is what is known as gamma convergence. So you want to show that this sequence of problems, this sequence of approximations converge. It's like in sort of in the sense of gamma convergence, but you also want to show that the rate of gamma convergence is related to the best approximation error. Okay, so that sort of gives you an idea of what kind of tools you need. And so there was a paper by Stefan Müller and Michael Ortiz, it's like a while ago, which talks about gamma convergence of variational integrators. And it relies on certain sort of technical assumptions, which we also need. So you need regularity of the Lagrangian in some closed and bounded neighborhood. You need that quadrature rule is sufficiently accurate. And the thing which is hard, or which requires some work, is you need that discrete and continuous trajectories minimize their actions as opposed to just extremizing them. Okay, so if you have all these technical assumptions, then you can show that this computable discrete Lagrangian, which I described, has the same approximation properties as this best approximation error of the approximation space. So that basically means that these things are optimal. Okay? So as I said, the critical assumption is action minimization. And so what you can show is that if you have Lagrangians of this form, quadratic kinetic energy minus potential energy, and if the time step is sufficiently small, then this assumption holds. So it just relies on going through the usual gamma convergence result and just being a lot more careful about, it's like the errors one makes. Okay, so that shows that your computable variational integrators are ortho-optimal, and that if you do this in a spectral way, they end up with methods which are geometrically convergent. Okay, so you can show that if you apply these methods, it's like to polynomial spaces of increasing degree, it's like, and you vary the time step, it's like then it has the rate of convergence, which is associated with the sort of the degree of the polynomial, which is not too surprising, perhaps. And then the other thing you can do is that you can sort of increase the polynomial order, but you keep the time step fixed. All right, and this is so this is what's happening here. You're letting the number of Chebyshev points increase while keeping the time step fixed. And here there are two curves. All right, so the first curve is the one with the circular dots, and that's the error at multiples of the time step. Right, that's the usual error analysis one does. It's like with numerical methods, you just look at how the errors behave. It's like at the discrete points. Okay, so that converges at this geometrical rate, which you expect. But if you recall, it's like when we constructed this computable discrete Lagrangian, I had chosen some element of the function space in order to compute the value of the discrete Lagrangian. And so you can ask whether that distinguished element of the function space is a good approximation of the solution in the interior of the time step from the interval 0 to h. And when you measure that error in the L infinity sense, you see that it is a good approximation. It converges at half the rate of the endpoint values. And this is that line here, which has half the slope of this other line, is the theoretical rate at which these continuous curves approximate the exact solution. And you'll see that for a long time, it's like the errors are right at the top of each other. And it's only when, in some sense, the boundary value, or at least the solutions at multiples of h are accurate enough, that you start seeing the slower rate of convergence of the interior solution, which are these crosses here. So what that more or less tells you is that if you have a polynomial space which is in some sense rich enough, that the interior solutions actually do a really good job. And so you can ask, well, what are the manifestations of this observation? So if you apply the you apply a numerical method, it's like to the n-body problem. So this is so the thing on the left is sort of the inner solar system. It's like with the full JPL ephemeris. It's like, and the thing on the right is, of course, the mathematical abstraction of this, right? The mathematical equivalent of the spherical cow, right? And you see that they have these nice little closed orbits. But what's significant about this simulation is that I'm taking time steps of 100 days, and 100 days is faster than the fastest orbital period in the problem. So Mercury is represented in the simulation. Mercury's orbital period of 81 days. So I'm taking a time step which is larger than the fastest orbital period. And nevertheless, I don't get absolute garbage, right? And the reason for this, if you will, is because these Ritz curves, it's like are good approximations of the solution in the interior of the time step, right? So you have enough approximation power, if you will, in these very high degree Chebyshev polynomials to capture it's like a complete orbit. Okay, and so that's some explanation for why this thing doesn't give you absolute garbage. And the same thing holds true. It's like if you do the outer solar system, and again here you've taken a time step of about 5 years, which is again faster than the effective orbital period of the problem which you have here. Okay, so you can look at what happens. It's like with these methods when you apply it to something simple like the free rigid body. The free rigid body has two invariants. It's like which is the norm of the body angular momentum. It's like which is associated with the fact that the spatial angular momentum is constant, and then the energy. Okay, so the evolution of this in body angular momentum coordinates is that it's on the sphere. It's like the body angular momentum sphere, and then it intersects with the energy ellipsoids. Okay, so if you look at mechanics and symmetry, for example, you'll see this on the cover of Mechanics and Symmetry. And so if you applied explicit Euler to this, it's like you'll see that it does a really poor job of keeping any of these invariants or respecting these invariants. If you use MATLAB ODE45, which is adaptive time-stepping method, and you really sort of crank up the accuracy, it's like by sort of making the tolerances extremely tight, then it does a much better job. But nevertheless, there is this slow drift that's like off the constrained spaces. Whereas if you sort of use these variational integrators and you combine them with certain Lie group ideas, then you see that they do a really wonderful job of staying on these constrained spaces. All right. So, okay, so that's a little bit of the ODE theory. now what I want to do is to try to use this to motivate what one needs to do in the PDE case. So hopefully you understand the take-home message of what we talked about, which is that this discrete Lagrangian plays a fundamental role in the error analysis and construction of variational integrators in the ODE setting. Okay? So what I want to do then is I want to use, I want to actually characterize what the PD analog of the generating function is. Okay? So that's basically what's happening here. So if you have type 1 generating functions or type 2 generating functions, you can define symplectic maps in terms of these generating functions. And it's easy to show that if you have generating functions, that the symplecticity property comes by just sort of taking the second exterior derivative of the generating function and then coupling it with the the definition of the symplectic maps. Okay, so we want to find a PD analog of this Jacobi solution, where you specify, you have a discrete Lagrangian, and it involves as its inputs the initial and final position. It's like on some interval in time. Okay, and then the thing which you give me is the action integral evaluated along a solution of the Lagrange equations which satisfy those boundary conditions. So the PD analog of this is quite simple. You want to specify now the fields along the boundary of a space-time domain. Okay, so this is what I mean by this. Okay, and I'm going to evaluate the action on some section which satisfies the boundary conditions and satisfies the Lagrange equation in the interior of that domain, right? So that's the natural analog of what I had before. Okay, so then the other question is, well, what's the analog of these kind of equations? So if you look at what you're trying to do, you're trying to take the variations of this discrete Lagrangian with respect to the boundary data. Okay, so I'll try to do that. I take this exact boundary Lagrangian or discrete Lagrangian, and I allow you to vary the field value at some point in the boundary of the space-time domain. And then I want to ask whether that's somehow related to the momentum. Okay, so it's not related to the momentum because the multi-momentum in the PD setting has n+1 times the dimension of the field. So it can't possibly be a direct equality. Okay, but what turns out to happen is that there's a way to sort of think of this right-hand side, which you get as being, in some sense, the normal component of the multi-momentum. It's like sort of normal to the boundary. Okay, really, you should think of it as a n+1 differential form, but if you give me a metric and it's like I make a few identifications, then you can interpret it in this way. Okay? So this is perfectly analogous. It's like what you get in the usual ODE case, and in fact, the sign it's like which you see here can be thought of as coming from the fact that the orientation of the boundary, it's like on the interval, it's like has this sign change, right? Okay. So this condition being satisfied, that's like on every point on the boundary of the space-time domain is the analog of this condition here, right? And so, and that's because here it's like you only have a time interval, and the boundary of the time interval are just the two endpoints. So you just have to specify this kind of condition at the endpoints. Okay, so what we do then is that so once you have this, you have a discrete version of Noether's theorem as before. You can again construct sort of group invariant discrete Lagrangians is using these kind of group-equivariant approximation spaces. And so you can ask, well, what the implications are for actually constructing an integrator for this. So the implications that are following, particularly in the context of general relativity, is that you want some sort of finite element, some space-time finite element, which takes values in the space Lorentzian metrics, and you want to do this in such a way that it's group-equivariant. Okay? So there are basically two approaches to doing this, which I'm aware of. One of which is this geodesic finite element construction, and the other one, which I'll describe, is joint work of Evan Gulick, is on group-equivariant interpolation and symmetric spaces. All right, so let's state that problem here. So you have the space Lorentzian metrics, so it's a symmetric 4x4 matrix with non-zero determinant and with sort of the following signature. All right, and then what you want to construct is that if I have some space-time simplex and I have sort of Lorentzian metrics, it's like at the nodes of that space-time simplex, I want a function that's like from the simplex to the space Lorentzian metrics, or the property that it's an interpolant. So if I evaluate that function at the endpoints or the nodes, it's like I recover the data which I was given. I also want that the interpolant actually stays in the space of Lorentzian metrics at every point in the space-time simplex. And I also want the property that if I transform the data by an element of the indefinite orthogonal group, right, which more or less corresponds to a change of coordinates with which it's like the space-time or with which the Lorentzian metric is defined respect to. If I transform, it's like that Lorentzian metric data, then I want that the interpolant respects that transformation as well. So this is the group equivariance part of the property. Okay, so let me just say why this is not so trivial. All right. So if you look at these two Lorentzian metrics, you can easily check they're both Lorentzian metrics because they have one negative eigenvalue and three positive eigenvalues. And if I do the component-wise interpolation of this, if I take the midpoint of these two things component-wise, then I just get the identity it's like matrix, which obviously is not Lorentzian. Okay, so naively interpolating Lorentzian metrics, it's like doesn't stay in the space of Lorentzian metrics. So one has to be a bit careful. All right, so let me describe it's like one systematic way of constructing sort of group equivariant approximation spaces. So this is the geodesic finite element approach, which is due to Oliver Sander and Philip Gross, right? And the idea is quite simple. So assume that you want to construct a finite element which takes values in some Riemannian manifold, okay? And what you want to do then is if I specify the data, it's like by this L superscript I, so imagine you have the data here, and then you have basically shape functions, okay? So the easiest example of shape functions to keep in mind are the barycentric coordinates on a simplex, right? So imagine these were barycentric coordinates and then these data points were at the nodes of a simplex. Then you want to minimize this convex weighted distance, it's like measure, okay, over the sort of data it's like in the manifold, okay? And because the scale valued shape functions typically satisfy a Kronecker delta property, when you're at the node it's like of the simplex, it's like all the terms vanish except for the distance between the data and your candidate point. So obviously what you want to do in that situation is to just recover the data which you were given. And so this kind of construction clearly gives you an interpolant. So this is what is known as the weighted Riemannian mean. One of the nice properties of this approach is that this is clearly going to be group equivariant with respect to isometries of the Riemannian manifold. And the other thing is that if you have shape functions with certain approximation properties, then this construction lifts now to an object which interpolates things in the Riemannian metric, in the Riemannian, it's like manifold, it's like with the same kind of approximation properties. So there's a way to lift, functions with certain approximation properties to sort of manifold valued things. So the problem with this approach is that it's extremely expensive to compute this because you really have to solve an optimization problem on a manifold at every point in order to evaluate this this shape function or this finite element. And if you put this in the context of a variational integrator, then you have to compute derivatives of this thing as well. So it gets very, very expensive. Okay. So I visited Philip Gross many years ago. It's like, and the first thing we did, it's like in the context of Lorentzian metrics, is to realize pretty early on that you can think of a Lorentzian, the space of Lorentzian metrics as a symmetric space. And then once you have that, there's a general construction which allows you to look at the induced Riemannian metric, it's like on such spaces. Okay, so that was how we started thinking about this. But as it turns out, it's like, as I said, it's like it was very expensive to compute these things. So, so we sort of adopted an alternative approach by using the fact that the space of Lorentzian metrics is a symmetric space. So let me sort of say what the idea is. So if the space of Lorentzian metrics was something like a Lie group, then of course one could make, one could construct it like these interpolants in a very easy way by using the exponential map, which would, and its corresponding logarithm, right? So if you have data, it's like in the Lie group, you take the logarithm to pull all the data back to the Lie algebra, do the interpolation of the Lie algebra, which is a linear space, and then exponentiate back out to the group, right? So if you had a Lie group structure, it's like that's sort of the natural thing one does. It's like in constructing group invariant methods. So of course, it's like, the space Lorentzian matrix is not a Lie group, it's a symmetric space. But, the critical component of this is a local diffeomorphism. It's like between the nonlinear space which you're working with some sort of corresponding linear space. And so it turns out that something similar to that exists, even though it's not a Lie group. Okay, so what happens is that the space Lorentzian matrix is diffeomorphic. It's like to the general linear group quotiented by this indefinite orthogonal group with this kind of mapping. Okay, and all right, and so what happens is that if you think of this quotient space, then every coset in this quotient space has a canonical representative. It's like using a generalization of the polar decomposition. So we came upon this by the realization that on symmetric spaces, there is the generalization of polar decomposition, and we had used the usual polar decomposition. It's like to do certain kind of interpolation methods. It's like for the rotation group. Okay, so anyway, it's like so a generalized polar decomposition decomposes an element of the general linear group, in this case to sort of these J-symmetric matrices, which are defined here, as well as something which is in this indefinite orthogonal group. Right? If you just had the usual polar decomposition, then what you would have had would be positive semi-definite matrices. It's like, and then sort of a rotation element here. Okay? So the log of this sort of J-symmetric space is a linear space. It's not a Lie group, but it's what's known as a Lie triple system. Okay, it's given here. But the main point is that it is a linear space. Bless you. So once you have that, okay, you have this J-symmetric matrices. You can take log of it to give you something which is in this Lie triple system. So this thing here is a sort of linear space. You have this quotient space construction, and then you have an identification between the quotient space and the space of Lorentzian metrics, and the explicit identification is given here. So basically now it's like given Lorentzian metric element, it's like you sort of essentially pull it back to this Lie triple system, do interpolation there, and then sort of push it back to the space of Lorentzian metrics. So that's really the basic idea behind this. So when the dust settles, it's like you end up with an interpolation formula which looks like this. And you, as with the sort of geodesic finite element construction, you have a choice as to what you choose. It's like for these scalar valued shape functions. Typically, again, they have this Kronecker delta property. But the upshot, again, is that if this scalar valued shape function has certain approximation properties, then this lifted interpolant, which takes values in the symmetric space, inherits those approximation properties. And that's really nothing more than a consequence of the fact that this is a diffeomorphism. It's like with certain regularity. Okay. Okay. So what this interpolant does is that it's signature preserving. So if you start with data which is in the space of Lorentzian metrics, it will stay in the space of Lorentzian metrics. It has this frame invariance, which I talked about, or frame equivariance if you prefer. All right. There's a symmetry under inversion, and there's some determinant averaging properties. Okay. And so we're not quite at the stage where we've put this, it's like in combination with the variational integration technology, but you can do something simple, like apply it to interpolating, it's like the Schwarzschild metric, which is this analytical solution of the Einstein equations. And you can then ask, well, what are the approximation properties when you do this? Okay, so if you have linear shape functions and you look at the L2 error of the interpolants, it converges at the right rate. And if you look at the H1 errors, it's like it also converges at the right rate. And in addition to that, as promised, when you do the interpolants and you evaluate the interpolant, it really does stay in the space of Lorentzian metrics. Okay, so you can do this with quadratic shape functions as well. It's like, and you have higher rate of convergence as you would expect. Okay, so there's a relationship between this and other methods. So one of the things is that if you, sort of modify the equation in the following way, you still get things with the same kind of properties. This is sort of the way to think about this more or less is that when you do this diffeomorphism, it's like you usually do this with a fixed base point. But if you allow the base point to move in some appropriate sense, then you end up with this other expression, and this interpolant is equivalent to the geodesic finite element interpolant. But with the advantage that now you can implement this using fixed point iterations, which are sort of interior point methods. So you don't have to stay in the manifold to do this. You just compute. It's like in the ambient space, it converges. It's like to the space of Lorentzian metrics. It's like in the limit, and so everything actually it doesn't even have to. Yeah, so you don't really have to even do this in the limit because, in some sense, it's like the log exponential thing sort of puts you in the right space. Okay, so and if you replace this sort of J matrix, it's like which is -1, 1, 1, 1 with the identity matrix, then what ends up happening is that you're now in the setting where you're looking at the usual polar decomposition into positive semi-definite matrices and rotation matrices, all right? And then this gives you the usual log Euclidean mean. It's like construction for symmetric positive definite matrices. Okay, so there's a general framework which I don't have time to talk about, but there's a whole sort of, it's like dictionary which sort of generalizes the things which you see. It's like for Lorentzian metrics to a more general case of symmetric spaces, and the usual thing happens. And in particular, it's like you can think of the generalized polar decomposition as being sort of the finite dimensional or the finite deformation analog of the Cartan decomposition of the Lie algebra, all right? And there's a nice sort of again general diagram it's like associated with this. And again, the upshot is that there is this sort of smooth local diffeomorphism between something in the symmetric space and this Lie triple system. Okay, so you can also apply this, it's like to the Grossmanians, it's like, and again, that recovers a standard method, it's like in the literature. So you can place all these specific techniques, it's like in this sort of more abstract framework. Yeah. So let me just summarize by saying that gauge field theories exhibit gauge symmetries that impose Cauchy initial value constraints, and they're also underdetermined. And so these result in degenerate field theories, and I've sort of briefly described why it might be beneficial to think of these kind of things, not in terms of the usual Lagrangian Hamiltonian mechanics, but in terms of multi-Dirac mechanics and multi-Dirac structures. I've talked about how you can systematically construct and analyze a class of variational integrators, and in terms of this exact discrete Lagrangian and the extension to Hamiltonian PDEs. And I pointed out that if you want to construct multi-momentum preserving variational integrators, a big part of this, particularly in the PD setting, is about constructing group-equivariant finite element spaces. And so for the specific application to general relativity, you can use the fact that the space of Lorentzian metrics is more generally a symmetric space, and you can use the generalized polar decomposition to construct these kind of group-equivariant finite element spaces. So let me just stop here. Thank you. Mm-hmm.
It's equivariant with respect to O1 or like local.
Sure, right.
Well, do you think that will be enough for 3GR, which probably has a much larger
right? Yeah. So, so the question is whether or not just having equivariance with respect to the indefinite orthogonal group is sufficient for general relativity. So essentially, it's like the idea is that you have this equivariance. If you will, sort of cell-wise, right? So simplex by simplex, and so the hope is that you could have something like a discrete gauge group by acting on the individual simplices in an independent way. Okay, so you might ask, well, how do you deal with that when you have sort of a conforming finite element space? So one of the things we've been thinking about is that because of the second order field theory structure, it might be more natural to look at the approximation spaces in terms of discontinuous Galerkian methods, where you think of the individual simplices as floating around and then having penalty terms. It's like, in order to sort of weakly enforce continuity. And that sort of addresses some, it's like issues with constructing basically, these scalar valued shape functions with enough regularity. So it's difficult to do this. It's like on a sort of unstructured mesh. It's like, and have enough regularity that you can do a sort of a fully conforming method. So again, the hope is that, by having just the approximation be sort of simplex by simplex and having that rigid transformation, that's enough to give you an approximation of the full gauge symmetry. Okay. Yeah.
I was wondering, in the Cartan approach, there's the basic variable to frame.
Sure. Right.
So it's basically the group is the general linear group, and you just declare that the frame is orthonormal. So
right.
that determines it with the right signature. So there's no any question about that. I wonder if that would simplify some of these interpolation problems if you use the Cartan frame.
Sure.
Instead of the metric.
Right. Yeah. So the question is whether or not you can, it's like use the Cartan frame instead of the metric. It's like to simplify the formulation. And I think we sort of briefly discussed this, that there are, of course, many ways of thinking about this problem. And yeah, I think it is certainly quite possible that if you took this Cartan perspective, that you would get something simpler. And to be honest, it's like we just ended up running of this just because it became amusing in its own right. It's like to be able to do interpolation on symmetric spaces and recover these existing methods. But we haven't really sort of spent a lot of time thinking about what the best way of formulating its like general relativity is. It's like, in a way which is then compatible with discretization. And part of this is because, this has been a hodgepodge of work, and simply because it's perhaps irresponsible, it's like as a numerical analyst to, sick your student, it's like on general relativity as a computational tool, right? So, so a lot of this has been, done in the context of trying to develop machinery which is applicable to other areas as well, but at the same time which, will hopefully be relevant to general relativity. So it's been difficult to sort of simply focus on GR. It's, I guess, the motivating application, and to the exclusion of everything else. And so we've always tried to develop methods which we think is potentially applicable to GR, but which has applications sort of broader as well. So that does sort of constrain, it's like what we can do in that sense. Yeah. Yes.
So if you choose your approximation space to be equivariant with respect to isometries, then does it turn out that your discrete action principle fits as a gauge group just the isometries, or can it be bigger than that?
Right. Okay.
This is related to the first question.
Sure. So yeah. So the question is, if you construct sort of these things using group-equivariant spaces, which were sort of equivariant with respect to the isometries, whether you end up with only something which respects the isometries and nothing else, right?
And what is the gauge group?
And what's the gauge group? Yeah. So yeah, so that's not so clear, right? I mean, it's like, so, so when I talked about these group-equivariant spaces, that's a sufficient condition for your discretization to be sort of group invariant. But I think more generally speaking, it's, whenever you have a field theory, it's like with infinite dimensional symmetry group, right? It's almost impossible to expect your discretization to respect the full infinite dimensional gauge symmetry. And so this is something you see in fluids as well, that at best it's like what you can hope for is that there's some finite dimensional analog, it's like of the symmetry group which is respected, okay? And so you can ask, well, is that enough? I mean, it's like to give you good numerical properties. So what you see is, and you can sort of understand this in the context of, the usual classical mechanics problem where you don't have the full time translational symmetry, but you have, I mean, it's like if you have a fixed time step symplectic integrator, you have a sort of a finitely generated subgroup, it's like of that time translational symmetry, which just corresponds to translations by multiples of the time step. So oftentimes it's like this finite dimensional version of that full symmetry is enough to give you good stability properties. It won't exactly preserve the momentum properties associated with the infinite dimensional symmetry group, But what oftentimes happens is that that Nova quantity, will oscillate, but it'll oscillate in a bounded fashion, right? So there's a, it's kind of a backward error analysis argument. And so this is, you can see this explicitly in sort of semi-discrete wave equations. So this is stuff which Claudia Wolf, it's like sort of Matt West and Marcel Olver did. It's like in the 1+1 semi-discretization, where they look at uniform spatial grids. It's like, and there's a spatial momentum which is preserved in the continuous theory, and it's not exactly preserved in the discrete theory, but again, it has this kind of backward error analysis stability. But so this is I think this is really a tough question. I think it speaks to the more general question of if you have infinite dimensional, it's like groups. It's like, is there a way of systematically constructing finite dimensional things, right, in sort of a graded fashion, which limit in some appropriate sense, while having, group-like properties, right? So this has been the problem when you're discretizing fluid mechanics, for example, and particularly when you want to do this in the context of discrete reduction theory. So, so the challenge, it's like in constructing discrete fluids from a variational perspective, it's like, in the framework of discrete reduction for Eulerian fluids, it's exactly how do you finite dimensionalize, if you will, the diffeomorphism group, while still having something like a group action on this. Yeah, so, so I guess what I'm trying to say is that there's no real hope of ever constructing discretization respects the full infinite dimensional gauge symmetry, but that maybe it's like some appropriate finite dimensional analog is sufficient. Yeah.